Okay, welcome everyone to the Markforged webinar. This installation is the complete metal solution. I'm Jon Reilly, the VP of Product. I'm here with Alexander Kreis, one of our content engineers, and we're going to walk you through metal printing from Markforged. If you have questions, there will be a opportunity at the end of the presentation to ask them. I don't think we'll get to all of the answers, but hopefully we can get through a few questions there. If we're not able to answer them on the live webinar, we'll both have a recording of it for everyone to review afterwards in case you missed something, as well as we'll try and reach out individually and answer everyone's individual questions. Okay, great. Let's get started. We'll start with a brief look at the agenda. I'll begin by introducing Markforged for those of you who don't know us. Then we'll talk about a customer case study and show you how they went from design to actual part. We'll review the return on investment and then the question section I just mentioned. Okay, about Markforged. We were founded out of MIT in 2013. We shipped our first printer in 2014. And our mission is to unlock the next 10x in innovation in design and manufacturing. We've grown a lot since we shipped that first printer. We now have a global fleet of printers. We're in thousands and thousands of printers in over 50 countries worldwide. Because many of our printers are networked, the network printers dial home and show us their IP address. You can see on this map sort of our global presence. So we're expanding further and further worldwide. And that growth has been driven because we're the only company to offer the full range of materials, from plastics to metals to fiber reinforced composites. But today we're going to focus on metals. So let's start with a customer case study. Dixon Valve and Coupling is a global manufacturer of hose fittings and accessories. They've been in business for over 100 years. They offer the broadest range of coupling products in the market. You don't survive 100 years as a manufacturing company without being innovative. Dixon Valve has sort of led the charge on moving to automated manufacturing in their industry. And that's been able to drive a great deal of profitability and flexibility for the product lines that they make. Today we're going to look at one individual particular problem that they're facing, which is an automated manufacturing cell that makes a steam pipe coupling. You're looking here at the pictures of the steam pipe coupling on a tray. These things are cast and then machined and galvanized. And the last step of the final assembly process is to put in a polymer crush ring, and they press that into the part before they ship it to customers. Unfortunately, when they machine these things, the insides of the couplings are incredibly sharp. You can see that the threads are present inside. Those are very sharp threads. And the way that they press in that crush ring, they use an automated cell. They have a robot arm with a gripper on it, which inserts into the inner diameter of the coupling, expands, picks it up, and moves it to the press fitting station. They press fit that polymer ring in, and then it puts it into the output flow, which you're looking at here. That sharp thread on the inside is really abrasive to the gripper on the end of that robot arm, so they're wearing through these jaws very quickly. They need to make them out of a hard material. If they need to make them out of a hard material, now they're machining things like stainless steel. That's slow, difficult, and expensive. And if these jaws wear or break, now you've got line stoppages. Dixon has a lot of flexibility in the types of parts that they make, so often they're changing out this tool as well as they're changing the shape or type of the couplings that they're manufacturing in this automated cell. So that's the problem that they face. Their solution requirements: they need a gripper jaw for the end of that robot arm that's robust, that has an incredibly high life cycle, high surface hardness, so that those sharp threads inside of the part don't eat it away. And then they need the ability to quickly change the nature of that tooling to minimize the downtime of this cell in their manufacturing line. Okay, let's look at the solution. The solution is 3D printed 17-4 gripper jaws. With the 3D printing metal technology from Markforged, they're able to go from art to the part itself the next day. They save $303 per gripper jaw You're looking at the picture of 3 of them here on each end effector, each robot arm. So that means over $1,000 per robot installation, robot arm installation. And then they save on average against their machine shop 19.5 days of time. That's because their machine shop is incredibly busy. They have one in-house, but they're primarily using it to machine high-value customer parts. So when they need tooling for the manufacturing line machined, they get in line and they have to wait. So now they're able to quickly and easily design gripper jaws for this manufacturing cell much faster and incredibly less expensive. All right, so to understand how that all works, let's go through the process one step at a time and explain how it goes. We'll start with an overview. You start with designing your part. You design the part that you want just the way you normally would in your CAD software. You print it on the Markforged Metal X printer. You bake it in an oven. There's a washing step between the printing and the sintering that we'll talk about, and then you're left with your final part. And so it's really a series of steps that go from design to part, and you can do that in by the next day. So let's go step by step. Step 1 is designing your part and uploading it into the Markforged software. You use the CAD software that you're familiar with today to create the part that you want. You don't have to worry about scaling because we handle that for you to account for shrinkage during the sinter process in our software. And then you simply upload an STL of that part to the Markforged Eiger software. And after you've designed and uploaded the part, it's really as simple as just hitting print. The part takes about 3 hours to print. I'm going to show you a series of progressive images of that part being created. We would have liked to show it as a video, but it doesn't come across on the webinar very well. Once you've hit print, the printer starts to print that part one layer at a time. What it's printing is metal powder, in this case 17-4 stainless steel, that's been bound in plastic. Unlike other traditional metal 3D printing technologies, that powder is now rendered safe because it's inside of a plastic binding system. We heat that plastic binder and print layer at a time. So here we will go through and watch that part be built one layer at a time, just like an FDM style part creation process that you're probably very familiar with. And 3 hours later, you have your part. The next step is to take that part and put it in the washing station. The washing fluid removes about half of the binding material. It takes about 9 hours to wash entirely through that part, cleaning out all of the half of the binder material so that you're left with a part that's sort of sponge-like, porous almost. At this point, the part is a little bit more fragile, but it's not like so sensitive that you could break it without trying. But it takes about 9 hours of wash time. It's important to note that you cannot overwash the part, so if you leave it in there longer, that's fine. The only problem is underwashing, so you want to make sure that the part is at least in the washing fluid the recommended amount of time. By the way, the washing station is connected to our software, as is the sintering station, which we'll talk about next. So we'll tell you exactly how long to wash it. We'll track that washing, and you'll get an email when it's done washing. So this is really almost as simple as running your dishwasher. You place the part in the basket, drop it into the station, close the lid, and come back and get the part back out when the timer expires. Once the part has been washed and that first layer of binder has been removed, you move on to the sintering step. You place the part on a ceramic bed inside of the furnace. We have 2 options of tube furnace available. You slide that into the hot zone, the uniform hot zone inside of the furnace, and you sinter the part for about 16 hours. During the sintering process, the part is run through a series of ramp and hold temperatures. The first hold temperature burns out the remaining binder material, leaving you with powder that is held loosely together. As you continue up the temperature ramp, those small metal powders start to neck into each other and then eventually sinter together, pulling into a part that shrinks by about 20%. And you're left with a final part that's fused up to 99.7% dense metal. The sintering time is about 16 hours, and that includes the time from placing the part and hitting start until the part is cooled down and is ready to remove from the furnace. You can fit multiple parts inside of the furnace, so depending on which furnace you pick, the Sinter 1 or the Sinter 2, we have larger or smaller sintering areas. So you can put as many parts as you can fit inside of that area for each sintering run. And again, the furnace is connected to our software, so we will monitor the sintering run for you while it's happening. You'll be able to log into the software to see where you're at in the process and how things are going. And when it's complete, you'll get an email that it's now time to go get your part. Okay, so here's the part on the actual gripper jaw in their line. Parts come off ready to be used. They have full isotropic strength. So if you're familiar with sort of layer at a time manufacturing and 3D printing, traditionally the Z-axis strength is a little bit weaker than the other axes because those layers are being built one at a time. But in the sintering process, you actually get crystal growth that goes across the axes. So your parts are isotropically strong. And then the part is just the metal that you chose to print with. So in this case, stainless 17.4. You can choose to do any type of post-processing that you would traditionally do on that metal. The tolerance is similar to cast. You should think about it like near net shape. So if you have a critical tolerance, you can just pop this thing in a CNC and polish up whatever that critical tolerance is to get it exactly right. And then here it is in use, locating that fixture on the rubber ring, the polymer ring you can see there at the bottom, that will then press fit that together for final shipping. Okay, so they were successfully able to print their gripper jaws. Let's look at their return on investment. When they were machining that part in-house, the cost was around $315. The all-up cost on the Metal X is $11.45 a part. That's about $6 of material cost, and the rest is allocated across washing fluid and the gas that is used to run the furnace to create the atmosphere inside the furnace during sintering. The savings per part then is like $303, which is 96.4% against their traditional manufacturing mechanism. And then, of course, time. Time is really critical in a manufacturing environment. They're now able to get their part by mid the next day instead of waiting around on the machine shop. That cuts down weeks of time from their process and gets them to about a 92 or 93% savings in time. So that's why this makes a lot of sense for them. They're able to accelerate their ability to react to changes, to change parts going through the automated line, and to replace broken parts incredibly quickly, and save a lot of money, about $1,000 an instance while doing it. So those are the crucial benefits. They get parts the next day. Their workflow is simplified. If any of you have worked with a machine shop in the past, often you need to cut drawings, dimension those drawings, then hand them off to be machined. Sometimes you need to create work holding fixtures. There's a lot of work that goes into having a part machined. Complexity is free with 3D printing, so it's a much easier problem. You go straight from the design to printing the exact part that you're going to need. That lets you get products to market much faster, and it increases your profitability of your manufacturing line. So the next webinar that we'll be hosting is going to take place on October 3rd. And in that webinar, we're going to tell you how this process scales from printing prototype parts to high volume production, all using the very same printing and sintering process that you've seen today. I'll give you a hint here that the answer is through parallelization. Just like computers have gone from large mainframes to farms of blades, this process will scale through multiple print head installations. We call them print farms that will be able to mass produce parts at scale, competitive with today's existing production technologies for metal parts. So you'll be able to use the same exact process to prototype, test, iterate, and then manufacture your final metal part. An invitation to that webinar will be going out on October 3rd. Okay, if you'd like to learn more, you can visit markforged.com/metal-x. And let's now go to the questions. Okay, bear with us here while we try and expand the questions pane. Okay, some people are asking again if the webinar will be recorded for later viewing. The answer is yes. Oh, okay, here's someone's asking if they can demo the Metal X software. So in, I think, 1 week, you will now be able to see the Metal X software working in Eiger. So you can go online and create an account It's a software demo tab that pops up on the right-hand side of the screen on markforged.com. You just have to put some information in because we make that account unique to you. Then you can upload your part. It'll tell you material times, center times, weight estimates, costs, etc. So you'll get all the information you need to know about your part. You'll be able to select stainless steel. Of course, you can also play around with using the other materials that we have, the composite materials and reinforcement. So I do encourage everyone who's interested to check out the software solution that can be found at markforged.com. Okay, we have some questions about the kind of washing fluid. The washing fluid is a thing called Opteon Scion. It's from Commerz. If you're interested in learning more about that, you can find some information online, or you can request it from us. We have safety data sheets and other types of information on it. The washing station takes about 8 gallons of fluid to fill, and you only need to replace that fluid you replace a few gallons of it about once every couple of months. And let's see, there's some other questions on the washing station. Is it an ultrasonic bath? No, the way the washing station works is there's a clean and a dirty tank. The parts are in the clean tank. The tank is constantly draining into the dirty tank. The dirty tank is heated to the boiling temperature of the fluid, which then evaporates above the clean tank and is condensed back into the clean tank. So the washing station is running a continuous cleaning cycle on the fluid, accumulating removed binder in the dirty tank. So when you're ready to change out that washing fluid, you just go to the back of the wash one, you open a valve that drains fluid out of the dirty tank, and then you pour more fluid in through the open top into the clean tank. Like I said, even under heavy usage, you maybe go through a gallon of that fluid like a month or two. And so even in-house when we're using the thing 24/7, I think it took us 4 months to use our first gallon, so that's probably a conservative estimate. You don't lose a lot of it because it's condensed carefully to stay within the machine. Okay, let's see, how do we deal with supports? Supports are printed in such a way that they're easy to remove post-sintering. There's 2 types of supports. There's printing supports and sintering supports. Both of those are designed to automatically make it so that your part is easy and ready to go out the back end of the sintering process. Okay, I'm going to keep going here. What kind of tolerances can I hold? The tolerances are similar to near net shape, so you can expect a few thou per inch. It's kind of dependent on part geometry. What kind of gas is required for the sintering furnace? Okay, there's 2 gases that go into the sintering furnace. The first is argon. You connect a dewar of argon, so incredibly cheap. That's used for most of the sintering cycle. And then for the critical part of the sintering cycle, where you're at like final sinter temperature, you use an argon with 4% hydrogen mix in the case of stainless steel. The gas mixture is always like that. It's either a forming gas or a argon. And that kind of depends on the material that you're using, but the sintering furnace will be capable of covering a wide variety of the materials we're going to be introducing. There's a question about the software. Does it know to scale the part correctly to compensate for the shrinkage? Yeah, of course. That's the trick of uploading the STL file, is then calculating what will happen as that part is then sintered, and making sure that we print the part that results at the end in a part that is exactly or as close to the shape of your intended end part as possible. Okay, let's keep going. Keep scrolling. When will aluminum material be available? So we'll be starting with stainless steel. I would expect aluminum sometime early next year. It's in beta now. Does the sintering time depend on part size? It can, but typically we're, for the sake of simplicity, I'm going to start by having a one-time sintering profile that's the same, because you could put a bunch of different size parts into the furnace. So we want to make it like really easy for users to ensure that they get a good result. Over time, we might look to introduce some software that helps us to tell which part you're putting in. You might be able to pick the part on the screen, for example. In that case, we could sinter the shortest time for your individual part. Okay, let's continue scrolling through. Let's see, what sizes of, oh, so for specifications, I'm sorry, If you'll look in the handouts section of the webinar, we've uploaded the data sheets for the metal printer, the 2 sintering furnaces, and the wash one. So a lot of these questions on the size of the print, the geometry limitations, things like that are all answered in those data sheets. I encourage everyone to take a look. And then that should cover most of the questions here, including the costs. Let's keep going. So what's this one? Okay, some people are asking if they're using third-party sintering furnaces, how will they know time and temperature to use? We'll share that information with you on the sinter profiles. One way to think about this is the post-processing, the washing and sintering technology is the same as metal injection molding, if you're familiar with that. There's plenty of production-grade metal injection molding furnaces that are available today. And so if you already have one of those furnaces and a washing station for parts for metal injection molding, then you're good to go. You don't need to buy those components of the solution from us. If you're doing incredibly high volume of parts, it's probably recommended that you have one of those production level solutions. Okay, let's keep going. Many of these we've already answered. The materials are stated in the data sheet, the ones that are in beta. At a high level, the way to think about it is any metal that can be powdered and sintered can be produced through this process. So the list of materials that we've been sharing today is very similar to the list of materials. It can be extended to cover the range of metal injection molding materials. So you can have like hundreds of different types of metal over time. We're going to try and prioritize the material introduction by demand. So if there's a specific metal that you're interested in, please let us know, and we will take that into consideration in the roadmap for materials. Okay, let's keep going. Someone is asking if more than one part can be put in the bath and the oven at the same time. Yes, you can put more than one part in the bath or in the sintering furnace. You can load those up to the full area of their working volume. And the software will account for the longest washing time necessary, dependent on part geometry. So again, it's kind of set it and forget it, but depending on the part that takes the longest to wash, we'll make sure that the rest of the parts wash for at least that long. And then the sintering run, as I mentioned earlier, is uniform. So for all the parts you put in, we're going to run the same full sintering profile to begin with, so that we're sure that the parts have good outcome properties. Okay, let's see, we're still scrolling through these. Some people are asking for information about heat treating parts. If you need to do a post-printing sintering heat treating process, you can do that just like you would on a typical part made of that material. Okay, let's keep going. How easy is it to switch metal materials? It's very easy. You just swap out the material cartridge with whatever material type you want next. You purge the nozzle a little bit to clean out all remaining of the previous metal, and now you're printing with your new metal material. Can you drill tap ream after sintering? Absolutely. You can do that. You can basically post-process these parts in the same way you would post-process the underlying material that you choose to print with. Okay, so I'm seeing a lot of repeat questions now. We're still scrolling through them. We'll try and take a couple more. Somebody is asking when the Metal X will be available. We're shipping our first systems to government clients this month. We'll be shipping more throughout the rest of the end of the year. If you haven't ordered by now, there's an incredible backlog. I would not expect to get your machine and system until early next year. Okay. Some people are asking if we sell the washer. Yes, we do. You can find the data sheet for the wash one in the handouts for the presentation. as well as the available materials. Sorry. Okay, and then it is worth noting, some people are asking about the environment for the printers and the washer and the sintering furnace. It's evident in the data sheet, but I'll state it here for fully accuracy, that you do need to provide ventilation at about 100 cubic feet per minute to the outside for both the washing station and for the sintering furnace. That's just to be sure that everything goes outdoors and is not in any way dumped into your working environment. This is pretty traditional in a shop environment. Okay, you ask, is the fluid byproduct toxic? This Opteon Scion fluid is sort of well known. It's a very safe fluid. They were regulated. These types of fluids were regulated a while back because they were damaging to the ozone. So this one was developed because it breaks down in sunlight. It doesn't have time to damage the ozone. So it's sort of a new generation of cleaning solutions that are actually more environmentally friendly. You do want to vent the drying station, which is the place where you put the parts to dry. That takes about 10 minutes after washing to the outside, which is there's a port on the back of the washing station. You just hook your ventilation up to. The stuff is heavier than air, but that just make sure that any remaining vapor from it is just vented outside of the building where it's dispersed. It's not particularly toxic. You can smell the material orders of magnitude before toxicity. So it's reasonably safe and easy to use. And your main objective is to sort of keep the lid closed when you're washing it so that you don't have a lot that's evaporating. And so it all works well and is safe. When you're disposing of the used material, you simply call for a chemical pickup. It's kind of like disposing of household paint. If you have any other chemical pickup going on, you already know how to do that. If you don't, it's reasonably easy to sign up for low-level chemical pickup creation services. We did that internally. It took us very little time, and it's very easy to just put this in a chemical container, and then someone comes and picks it up. Okay, I think that's probably enough questions for now. We're seeing a lot of repeat questions in here, so it's hard to parse through the others. If you have asked a question that we didn't get to, we are going to come back and try and answer everybody. So expect us to follow up via email or from a phone call to help answer your individual questions. Thank you very much for attending the webinar, and I look forward to having you on the next one where we talk about scaling from prototype to production. Thanks, everyone.